Hey everyone, and welcome to Chapter 4 of the KIS VCE Chemistry course. In this chapter, we're going to be changing our focus a little bit and looking at redox reactions. For the past few chapters, we've done quite a little bit of work regarding fuels and combustion reactions, and today we're going to look at a different type of reaction. We're going to look at redox reactions. Now, you might remember redox as one of the reaction types we learnt about ages ago in our very first revision chapter. And now we're going to go into a lot more detail about them. We're going to learn about what redox reactions actually are, and we're going to look at one of the important skills we need to know when dealing with them, which is oxidation numbers. One thing to note about oxidation numbers and a couple of the next few videos is that I'll be going through a lot of processes. It's important for you guys to have a good understanding of these processes, but the problem with that is as we go through these individual processes, a lot of them will seem kind of mutually exclusive and you won't really understand how to apply them. The thing with redox reactions is that you need to understand multiple different types of processes, and then towards the end of the chapter, we'll see how to put them all together. So, for the next few videos, hang tight, watch them, do your best to understand the different processes that we're going to learn, and then towards the end, I'll give you guys a really good overview of how they all integrate together for redox reactions. So let's get started. Chapter 4, what are redox reactions? So redox is actually a shortening of two words. Redox reactions stand for reduction and oxidation reactions. So in redox reactions, we're kind of talking about the combination of these two reaction types, reduction and oxidation. So what are redox reactions and what are reduction and oxidation reactions? In general, redox reactions involve the transfer of electrons, which I'll be denoting as E-, and this applies to both reduction and oxidation reactions as well. So in redox reactions, what we have is we have a reductant transferring an electron to an oxidant. And the combination of these two phenomena, reduction and oxidation, is what we call redox. So, when it comes to redox reactions, as I've already told you, they're comprised of both reduction and oxidation, and we call each of these half equations. Reduction is one half equation, oxidation is another half equation. So, we can say that a redox reaction is comprised of two half equations. We have oxidation, in which, now this part's important, we have a loss of electrons, and we also have reduction. Once again, important because we have a gain of electrons. Now, the way that we like to remember this is via the acronym OIL-RIG. And what does this stand for? OIL-RIG stands for oxidation is loss and reduction is gain. So make sure you guys remember this acronym because it'll come in handy quite a lot over the next few chapters. So just remember OIL-RIG for now. Alright, let's move on and talk about oxidation numbers. So now that we've got a decent understanding of what redox reactions actually are, a transfer of electrons caused by two half equations, let's learn our very first skill. So we're going to be learning about oxidation numbers. As I've said already, this is going to be a reasonably difficult skill to implement for the overall bigger picture, but let's focus on that towards the end of this chapter. For now, let's talk about this individual skill and why it's important. So oxidation numbers are key for us when it comes to identifying redox reactions. What we can do with these is use oxidation numbers to identify whether a reaction is oxidation or reduction. So we can help us determine what type of half equation we're talking about. Now, oxidation numbers are theoretical, and this is really important. Oxidation numbers are theoretical numbers that we simply use as tools. They don't really have any real-world application. So we're not talking about something like 3 grams, in which the 3 might be representative of a weight. We're not talking about charges such as +1 or -1, which might be indicative of our valence electrons. No. In this case, when we're talking about oxidation numbers, these are purely theoretical and we only use them as tools to work out whether something is reduction or oxidation, not for anything else. So let's go through the steps and then do a couple of quick examples. This is what you guys will need to do when it comes to oxidation numbers. Step number 1, elements by themselves have an oxidation number of 0. So, an example of this is if we're looking at something like nitrogen gas, N2. As you can see, we have nitrogen all alone. It's an element all by itself, and thus it's going to have an oxidation number of 0. That's our first rule, our first step. Our second step is that ions have oxidation numbers equivalent to their charge. So if we're talking about an ion such as, let's say, calcium, so Ca2+, which we know is the cation calcium, this is going to have an oxidation number of +2. So the oxidation number is equivalent to its charge. Now here's number 3. Oxygen is usually assigned an oxidation number of -2. However, there are some exceptions, and these exceptions are: number 1 is the main exception, for oxygen is that if it's found in a peroxide compound. So the most common kind of peroxide that we might be aware of is hydrogen peroxide, which is bleach. So this would be something such as H2O2. And in these cases, it has an oxidation number of -1. For oxygen. So usually it's -2. However, if it's in a peroxide, it's going to be -1. Now, our next rule, number 4, hydrogen is usually assigned an oxidation number of +1, but once again, there is an exception. And that exception is that when hydrogen is found in a metal hydride, then its oxidation number is -1. So this could be something such as sodium hydride, such as NaH. And in this case, it'll have an oxidation number of +1 for hydrogen. So that's just one exception. And then finally, number 5 is that all molecules should sum the charge of the product. So what this means is if we take a look at a molecule such as Cr2O7 minus, the 2 minus applies to the entirety of Cr2O7. So the entire molecule should be the sum of all of the individual parts within it. So -2 should be the sum of all the individual parts within it. So let's do a couple of examples so that we can get an idea of how this works. I'll just move over to the side here. Actually, I'll do it over here so that you guys can still see the rules. Let's do a couple of examples. Let's start out with CO2. So let's work out the oxidation number of the C in CO2. So whenever we're finding oxidation numbers, they are always going to be for an individual element within a larger molecule, or sometimes just an individual element on its own. So in this case, we're trying to work out the oxidation number of C. So let's work out a couple of things. What is going to be the overall charge of CO2? As you can see, it doesn't have any +2s or -2s or anything like that here. So according to rule number 5, the entire molecule is going to have a charge of 0. And 0 equals, so it's going to equal the oxidation number of C plus 2 times the oxidation number of O. And as we know, what is the oxidation number of oxygen? It's -2. So we can say 0 equals C minus 4. So what can we conclude? Our value for the oxidation number of carbon is going to be +4. That's our oxidation number. And make sure in these cases as well to always write a charge in front of your oxidation number, regardless of whether it's positive or negative. Now let's do another example. Cl2. And we're trying to work out the oxidation number of Cl. This is quite an easy one, as we can see that it's chlorine on its own. It's an element alone. So according to rule 1, Cl is going to have an oxidation number of 0 in this case. So as we know, according to rule 5 again, it would have had a total charge of 0, and Cl is going to be 0, so it would have just been 0 equals 0. Okay, so that is the value for chlorine. And one other thing I want to note, oxidation numbers for elements can change depending on the compound the element is found in. So just because Cl has an oxidation number of 0 in Cl2 doesn't mean it's always going to be 0. Depending on the compound we find it in, it could have a different oxidation number. So let's take a look at C. Let's work out the oxidation number of calcium in calcium oxide. What's the overall charge here according to rule number 5? It's going to be 0, and 0 equals our calcium value plus 1 of our oxygens. And what does oxygen have a oxidation number of? -2. So we can conclude that calcium has an oxidation number of +2 in this case. I'll just write that in light blue. Now moving on to example D, let's do C2H4. So according to rule 5, once again, it's going to have a total of 0 as its oxidation number. Now we have 2 times carbon, and we're going to try and find out carbon because that's the one we don't know. And then we also know that hydrogen has a oxidation number of +1. So it's 2 times the carbon value plus 4 times 1, or +1. So in this case, we work it out to be 0 equals 2C plus 4, and thus the oxidation number of carbon equals -2. All right, now let's move on and do question E. Let's take a look at NO3-. So NO3- is an anion, as we know, with a charge of -1. So according to rule 5, we need to remember that it's going to have an overall charge of -1. Thus, let's work out what it should be. The one we don't know here is N, and we want to find that out. So N is going to just be shown as N plus 3 times oxygen. And what does oxygen have an oxidation number of? Again, -2. So -1 equals N, -6. And so nitrogen is going to have an oxidation number of +5. And that's going to be our answer. And now let's finally do F. Here we're talking about H2SO4. And we want to find out S because it's the unknown one. And in this case, according to rule number 5, we're going to be talking about a total oxidation number for the molecule of 0. So that's going to be, sorry, not oxidation number, it's going to be the charge for the entire molecule. So 0 equals 2 times +1 for hydrogen plus S plus 4 -2 for oxygen. Then we're going to get 0 equals 2 plus S -6. And so our, sorry, not -6, -8. And so our total oxidation number for sulfur here is going to be +6. There we go. So +6 is going to be our answer. And finally, let's do one more example. This is a bit of a tougher one. Let's do Cr2O72- like we talked about before. And we're trying to work out the value of Cr. So according to rule 5, we're going to have a total charge for this molecule of -2 because it's an anion with a charge of -2. And that's going to equal 2 times the Cr oxidation number for chromium. And then we're going to also add 7 times -2 for oxygen. So we're dealing with -2 equals 2Cr -14. So -2 and 14 gives us 12 equals 2Cr. And finally, our oxidation number for Cr equals +6. All right. So hopefully those few examples will give you guys a few ideas about how our oxidation numbers work. Just realized I got the alphabet wrong. There we go. And what I want you guys to get out of this video is pretty much understanding the main steps for working out oxidation numbers, as well as a general overview of what redox reactions are. So the main things you need are to memorize your oil rig, and also just to understand that redox is a combination of reduction and oxidation and involves the transfer of electrons. As we go on and learn this in more detail, eventually the understanding will come to you guys and you'll have a full, comprehensive view of oxidation and reduction. So that's all for this very first video. Hopefully that all made sense. As always, if you've got any questions, please leave them down below.